everybody. Good morning and welcome to the 24th Meteorological Virtual Seminar, which is hosted by the Ghana Meteorological Agency. And today we'll actually be speaking on the topic solar radiation management with stratospheric aerosols interaction with Harmattan and associated potential impacts on temperature over Southwest Africa. And with this topic, it will be treated by one of our able professors who has a PhD in climatology from the University of Cape Town, South Africa. Her research focuses generally on the atmospheric physics and particularly on climate dynamics, modeling climate impact assessment. She has worked on both national and international projects and consultancies involving the climate and health projects in Ghana and the ongoing Codex experiments, the ECOWAS as the WMO consultant on National Framework for Climate Science for Ghana. She is a lead author in Working Group 1 for the Intergovernmental Panel on Climate Change Seat Assessment Report. Also, she has co-authored a good number of journal articles and publications to her credit. She's also the AIM's Canada Research Chair in the climate change science field. The project she's embarking is on focusing on understanding climate dynamics of Africa, climate observations, and projects for climate services. She's also an associate professor and the head of department for the physics department in University of Ghana, Legon. She's actually in the person of Professor Nana Ama Brown Kluche. Professor, please, you're welcome.
Thank you.
Please, you can actually start sharing your screen so you start with the presentation.
Okay. In a moment.
Okay. Please, before she starts sharing her screen, I'll urge everybody to jot down the questions they have so that at the end of the presentation, we can actually ask our questions and our inputs to her research work. Thank you very much.
Okay, so if I do this, does it come on full screen? Hello.
Yes,
Hello.
please.
Yeah.
We can see the full screen.
We can see.
Thank you. Good morning, everyone. Thanks for the opportunity, Samuel, Daniel, Jimet, organizers of this seminar series. So as introduced, going to talk to you about solar radiation management with stratospheric aerosol interactions with Harmattan over Southern West Africa. So I'm currently the head of department and also the vice chair of Working Group 1 of the IPCC. I work on this project with a team, and I will introduce the team in the next slide. But I also want to give recognition to the funders of this project. So this project is funded by the Degrees Initiative, and that is an NGO that is dedicated to putting the Global South, where Ghana, Africa belongs, at the center of the solar radiation modification. So I will give first introduce my team, and then we'll go ahead with the talk itself. So as I said, I work with a research team on this particular project. Dr. Azoda Hubert Kofi is a senior lecturer at the physics department, University of Ghana. His research is focused on energy physics and influence of climate change on solar energy and all that. Dr. Mayor Kwenom is from Benin. He's doing interdisciplinary research. He's into climate modeling, but has a background in physics, hydrology, meteorology, and climatology. We have Dr. Atanas Dumont, who is from Cameroon. His PhD is in atmospheric science, and he specializes in clouds microphysics, cloud variability, and impact on climate system. In the team is also Dr. Pesikwe Green, who is a lecturer at the University of Cape Coast. He's also doing research on climate dynamics over Africa. Dr. Francis Nkrumah is also a lecturer at the University of Cape Coast, and his focus is on climate dynamics and looking at extreme events as well. Dr. Patrick Essien is also a lecturer at the University of Cape Coast. He's focusing on the upper atmospheric dynamics and impact of atmospheric disturbances on climate system. And we have a student who works with Ghana Meteorological Agency, who is an MPhil student at the Department of Physics, University of Ghana. Her research is looking at climate variability that is due to changes in solar radiation or solar irradiance over southern West Africa. So I hope Becky is on here. Her work is directly about this project. So she's the student on the project. The rest of the team members are researchers, and so they're already having their position. So on the background, we experience Harmattan in Ghana. And we experience Harmattan also in the West African region a lot. And those of us here can remember that during Harmattan, we get a cooling effect. And so we need scientific explanation to that cooling effect, what Harmattan is and why we get a cooling effect. So, and that Harmattan is a natural occurrence in the climate system or in the atmosphere, and that gives a cooling system. Today, we are all battling, advocating, talking about global warming, and temperatures are rising in every region. Ghana's temperature has changed significantly, has increased, let me put it that way, increased significantly. So if we have a natural phenomenon that gives a cooling effect, why don't we do more research on it and see how we can get this cooling effect all year round? So my research is to use the effect of Harmattan and find ways of replicating Harmattan, putting it in a simple language, replicating Harmattan all year round if the climate system will be more favorable for us in West Africa. So during Harmattan, we get injection of dust particles and aerosols into the atmosphere. So we have volcanic eruption that is called Pinatubo volcanic eruption that occurred in 1991. When that eruption occurred, we had a huge release of sulfur dioxide and other aerosol component into the atmosphere, specifically into the stratosphere. The world recorded a cooling in that year and subsequent years. So that's also a natural cooling effect from aerosols and from a volcanic eruption. So we know that in a natural sense, when we get aerosols into the stratosphere, it results in some reduction of temperature. In physics, we see that it reduces the amount of sunlight that is reaching the Earth's surface. And if the amount of sunlight reaching the Earth's surface reduces, it naturally reduces temperature or the heat or the amount of temperature that we receive on Earth. And science has shown that the stratospheric injection can reduce 10% of sunlight that is reaching the Earth's surface. So still on the background, solar radiation. So once we have the aerosols injection into the atmosphere, it manages or changes solar radiation effects, or we call it solar radiation forcing on Earth. It is quite clear how temperature will be or is with the injection of aerosols in the atmosphere. So when we have Harmattan, we clearly get cooling effects. So that we get. We are not sure how this effects affect rainfall or how rainfall responds to the solar radiation management. That is still uncertain and it's open for research. And that is one of the things we are doing at the University of Ghana on this research. So we try to understand how these aerosols in the stratosphere affect climate variables and how it can help us to mitigate the effect of climate change. So our project focuses on the combined effect of solar radiation management, Harmattan, on climate variability in Southern West Africa. Harmattan. Most of us, anybody who grew up in Ghana or in West Africa might have experienced Harmattan or should be able to tell us something about Harmattan. We know that it's normally windy or a wind that blows over sub-Saharan Africa during December, January, February period. Sometimes the onset is a bit early in November or early part of December. Other times it's a little bit late. Sometimes it extends to March. Other times it cuts very early in January. So the Harmattan itself, the season has variability. So these winds are normally dry and they migrate from the north to the south within the West African region. And it has a lot of effects on the climate system. So we'll go through that in the project. So still on Harmattan, there are a few things that we know. That we have dry, hot wind that blows from the north, and it shifts the intertropical convergence zone. It has a lot of effect on the climate system, as I said earlier on. So this big graph of Africa here shows the green portion is normally our rainfall zone, low pressure system that gives us rainfall. And there's a black line that shows what has written intertropical convergence zone on it. So we have the wind system that blows from the Atlantic Ocean and into inland. And then we have that part of Harmattan when that blows from the north. So the emergence of these two wind systems, where they converge, we have a low pressure system that normally results in rainfall. So we have during the June to September season of the same wind, and it's a little bit weak. But then during December, January, February to March, thereabouts, these Harmattan winds are normally strong and they push the intertropical convergence zone further down and it shifts rainfall. So we don't get much rainfall over the western part of Africa. But then during the June to September season, we get rainfall over the western part of Africa. So a bit of this is a bit of the dynamics that the Harmattan winds and also the winds from the Atlantic Ocean also give us in over the years. We know that during Harmattan we get wildfires because the winds are dry and it's easy to ignite or once we get fire, for fire to spread in the forest. During Harmattan, we know there's influx of dust in the atmosphere, and so we get low visibility in the atmosphere, in the skies. So normally during Harmattan, when you have to drive at dawn, it's not safe because you cannot see very well on the road. But of course, we also know that we get dust on our faces and our bodies when we are out there during the Harmattan season. So these are a few things that we know during the Harmattan period. The less we know also about Harmattan is the extent Harmattan modifies the solar radiation in the atmosphere. So the extent to which the sunshine from the sun reaches the earth get modified during Harmattan season because of the dust, because of humidity changes. We don't have much knowledge on that. But we know that dust has significant impact on the biochemical cycle of solar radiation and the Earth climate system. The Harmattan effects affect the radiative forcing by reducing the amount of sunlight that reaches the atmosphere. So it's like a way of blocking sunlight from reaching the Earth's surface. Any change in the solar radiation causes changes in the climatic parameters. So for humidity, for temperature, for rainfall, whenever there's a change, we know that the solar radiation is the major energy input of the Earth system, of the Earth climate. So any change, however small, that the radiation gets reaching the Earth causes changes in climate parameters. Harmattan winds also results from changes in wind direction during the year, as earlier on. And these winds are expected to be initial cause of a possible Harmattan outbreak. A large enough wind speed can cause dust particles to be injected into the atmosphere. And once the dust is in the air, they travel in the same direction of the wind. This we also know. So the Harmattan will blow wind, the Harmattan will blow, or wind will blow with the dust in the same direction the wind is blowing. The research activities on this project, we have examined the influence of stratospheric aerosol injection on the driving mechanisms of Harmattan. So we know Harmattan, causes of Harmattan, but we also want to know how extra stratospheric aerosols in the atmosphere will change or will constitute changes in the drivers of Harmattan. We also examining the influence of solar radiation management on the Harmattan season itself over the Western or the Southern West Africa. And we are assessing the potential impacts of such a radiation management on rainfall and temperature changes over the Southern West Africa. For this presentation, I will focus on wind and temperature. We are still working on the rainfall responses to the solar radiation management. We have used two data sets and two main data sets. The ARISE data set is assessing responses and impact of solar climate intervention on the Earth system with stratospheric aerosol injection. So it's called ARISE SAI. We use also the community Earth system model, version 2, with the whole atmosphere community model. So that's version 3. So it has a very long name, CSM2 and WAC 6. So these two models we have used to assess the ideas of dust influx and the effect on temperature, rainfall, humidity, and other climate parameters, also wind. So clearly from the two data sets, the community model and ARISE. So ARISE is a model that has aerosols in there. So the blue is the ARISE data set with aerosols, and the red is a climate model data without aerosols. So this is a figure showing temperature over the current years and the future years, because the ARISE data set is only for the future. So the model data, which is the SSP2 4.5, shows both the current years and the future years. So just for you to appreciate the effects of aerosols on temperature in the atmosphere, like the same feeling we have during Harmattan season when we have dust in the atmosphere. We have ARISE having aerosols and giving a cooling effect. So you can see that temperature is low compared to SSP2, which is a model without aerosol. So you see high temperatures of the SSP2 and low temperatures with ARISE data set when you compare the two. And this is during the Harmattan season in December, January, February over West African region. So this is just a background figure to give you the background to the main discussion. Okay, so this is assessment of dust itself as PM 2.5, which is mostly the dust particles, the size of the dust particles we get in the atmosphere during Harmattan. Of course, we have smaller amount of dust, which I will also show pictures for during the Harmattan season. And we have done this from example of models. So here, the first figure shows the dust, amount of dust, PM 2.5, the concentration of this dust during the Harmattan season over the years. So from SSP2, which is the model, and also from the ARISE data set. So you can see that we have we have PM, dust particle PM 2.5, almost equally represented in the two models that is shown with this line graph. So when you compare with the spatial figures here on the right side, it's also showing December, January, February at the mean low level. So this is at the 925 hectopascal level. It's close to surface. And we try to assess the difference between the two models, the SSP2 and also the SI. But the first panel shows the current, and so we subtract the most current years, 2020 to 2039, from far future, 2050 to 2069. So this shows a change we're going to have in future, or what we call climate change, in terms of dust particles. We did same to compare the ARISE with the model data set in the second panel. And you can clearly see the difference in the dust, where it is mauve color, it's less dust, where it goes brown or deeper brown, it's more dust concentration in the model. So we did the same also for different sizes of dust. So the first one you saw PM 2.5, that's a little bit big. But then here we have the other sizes of dust concentration, which in the left part of the figure, you see dust concentration still also in the December, January, February. And you can see that there's still virtually the same amount of dust in the two models, except for a rise towards the end of 2070, which shows low amount of dust concentration. But when you take the spatial concentration of dust, you also can clearly see the difference in the change. Please, you can pay attention to the years that is showing here. 2035 to 2054 minus 2020 to 2039. This is to understand how the future changes in dust concentration will look like when we model them. But then the last panel, which is the B and D, shows the difference in the arise and the difference in the model without stratospheric injection. So we see that there's more dust concentration. So the more brown it is, the more the concentration. You can see that there's some differences that's shown from the two models when we do the spatial differences. This, it's still PM 2.2, 2.5 at the vertical profile. So we want to know how the dust is profiled in the vertical column of the atmosphere. We start from the very ground where we walk up to a certain level in the atmosphere towards the stratosphere. So in the right part, we have PM 2.5 at some pressure levels, but from the ground where we walk up to a height that is 800 hectopascal in the atmosphere. So this goes beyond the stratosphere, goes into the stratosphere. So we want to know how it's also profiles in the stratosphere compared to the troposphere. And the first one is the difference between, like we saw earlier on, 2035 to 2054 from the 2020 to 2039. And then the second one is it's the same profile at the same pressure levels from ground to the top, also from checking the climate change over the column of the atmosphere. At the left side, we also see the spatial, but in a cross section of, so instead of the lines here, we have it using pictures just to appreciate where we have the concentration more, where we have less concentration in the stratosphere, from the troposphere into the stratosphere. So this is still dust concentration like we saw earlier, but these are different sizes of dust in the atmosphere. So we have about the same, and the trends are looking virtually the same. So this is the distribution of maximum temperature during the Harmattan period and over West Africa. So we have this in the baseline climate. So the model itself without stratospheric injection minus the baseline climate produces or gives us a maximum temperature of a distribution like this. For near future, 2035 to 2050, and then we have for far future, 2050 to 2069. For this middle panel, we have the arise, which is the model with stratospheric aerosol injection, subtracting the baseline from it, and you can see it gives much less temperature or much less maximum temperature compared to the model without stratospheric injection. The last panel is the difference between the two, the model and then the arise. So this just to give you the essence that when we have aerosols in the atmosphere, it gives a cooling effect. This is projected changes in wind speed characteristics over the region during Harmattan. And the first figure you saw of Africa and how the wind system looks like during the June to September and December to February season. It's about the same graph. So this shows from Arise and from the model, and this is December, January, and February. The red line is the intertropical convergence zone line we saw earlier on. So this helps us to see where we have a push of the intertropical convergence zone from the wind system over West Africa. So this is wind speed in the colors. So the bluer it is, the higher the speed. And the arrows shows the direction of the wind. And of course, the length of the arrow also shows the magnitude of the wind. So it's clear, shows the direction of the wind here. And below it, or where we have, if you can see my cursor, you can see that there's influx of wind from the Atlantic Ocean up, and then we have also the influx of wind from the northern part up. So where these two wind systems meet, we have a low pressure system that supports rainfall and thunderstorms over the region. So this also demonstrates that December, the intertropical convergence zone is still lying over the region around Ghana. Let me put it that way. In January, it goes down a little bit into the ocean, towards the ocean. In February, you don't even get to see it, that it goes a little bit more down. So December, January, February, we normally do not experience rainfall over our region, especially in January and February. These days, things are changing, and so we see that we are getting rainfall in December. I think last 2 years it rained heavily in December. Last year it rained a little bit also in December. We can even see a glimpse of that even here. But of course, this figure is far future figures, not current figures. So this is for Arise, and then this is when we have stratospheric injection, and below is for the model without stratospheric injection. We have the wind speed also plotted at the vertical profile. So when we have the zonal and the meridional winds. So this is the zonal wind, and we looked at it at the vertical profile, and then we also looked at it period, and we looked at it we looked at the spatial differences.
No, I can't feel it. No, what driver am I friendly?
You can mute this guy. The spatial differences in the model and the arise. So when you look at the wind speed here, you see that for model, this is the change where we have 2035 to 2050, and we subtracted the most current years from it. So the two panoramas shows the change. When you compare with how Arise So arise and the model difference also shows in the last panel here. So we have some differences in wind speed when we have stratospheric injection of aerosols. Yeah, so this is still zonal wind plotted in another way. So you can see the difference, model and arise. Not much difference in the wind, zonal wind, when you plot the time series. And when you get to the spatial plot of the zonal wind, we see some significant differences in the plot. So the same trend as we saw before. This is ozone. Ozone, because we know that when we have dust, I'm sure most of us heard about the depletion of the ozone layer. So when we don't have, or when we have some gases in the atmosphere, they react with the ozone. Ozone is O3. O3 is an unstable oxygen. So O3 is unstable oxygen. So it reacts easily with other gases. So when we have a gas like carbon monoxide in the stratosphere, remember ozone is concentrated in the stratosphere. So when we have carbon monoxide, for instance, in the stratosphere, it reacts easily with ozone, and ozone changes to oxygen and carbon dioxide in the atmosphere. So it removes the ozone. So there was a time we heard a lot about our fossil fuel, or when we burn, we are removing the ozone layer. Okay, so the ozone is there to also shield or absorb the solar radiation from reaching the surface of the earth. So it has a huge radiative effect on the earth climate system. So we decided also to assess the ozone of the atmosphere, and that is also in the stratosphere. So how the two models also simulate ozone is also shown here. You can see from the first figure of the time series that they have competing almost similar ozone, amount of ozone in the atmosphere over the years. And when you look at the spatial figure also, it shows how much ozone will be like in future, the changes we are having in the ozone. And when you subtract the model from the arise data, the arise again is when we have injected aerosols in the stratosphere. The ozone is in the stratosphere, and so it will have direct effects on the ozone. The aerosols have direct effect on the ozone. So we needed to also understand this, how the ozone will be like or is like with the stratospheric aerosol injection. So this is a way to understand how solar radiation reaching the atmosphere and reaching the earth will control or will affect the climate system. And as I said earlier on, any change in the solar radiation affects so many things in the climate system. It affects temperature, it affects rainfall, it affects wind, it affects humidity. And so the subsequent effects, or consequentially, it affects the climate system, and it affects the weather system as well. So basically, that is And this is also the vertical profile of ozone. So even within the stratosphere, which is a layer, we also try to understand how the ozone will look like now and in the future. So I think that is it. And once I'm coming from the IPCC, I'm also happy to introduce the IPCC system to your audience and also show the many layers or levels that all of you or any of you can contribute to the IPCC system. So we have a focal points in different countries, the IPCC. And if you want to be contributing to the IPCC, your focal point should nominate you. And there are many levels in the IPCC you can contribute to. Getting into the IPCC system, the system must know you through your publications. And I believe there are a number of researchers here. Do quality research, do a lot of research, publish your papers. The IPCC system will know you, and you are knowing the IPCC even from now and from here. You can jump onto the IPCC website to read more about it. You can be a member of the Bureau like me as a vice chair of the Bureau of the Working Group 1. You can be working as secretariat, member of the secretariat. You can be a member of the steering committee, lead author, contributing lead author. You can be chapter scientist, review author. You can be called to contribute as an expert in scoping meetings. You can contribute to technical support unit and can also be a member of the task team. Most of these levels or contributions are voluntary. Only the secretariat gets salary and the technical support unit gets salary. Even chapter scientists get stipend. The rest of the work is voluntary. So the IPCC system has always been voluntary. But there are many advantages that you get when you contribute to the IPCC system. There's prestige that you get. There's other opportunities like funding you get, gives you visibility, and it puts you, of course, your research out there. You can discuss your interest with me, with any expert or scientist who already know or is in the IPCC system. But you can also read about it online. They have their website. I used to say that anyone can be a part of the IPCC system if you're a natural scientist, earth scientist, meteorology, archaeologist, any area, social sciences, education, you're doing art, media, communication, policy. If you're doing advocacy, you can contribute to the IPCC system. Personally, I have contributed so many ways in the IPCC system. But then if you need your paper cited, do quality research, publish in quality journal, target deadlines. IPCC normally publish the literature cutoff for deadlines, and encourage yourself, your students, your colleagues to contribute or participate in IPCC activities. And you should collaborate with other scientists. So my personal experience in the IPCC, personally, now I am the vice chair. I worked as a lead author in the state assessment report and worked on Atlas and did interactive Atlas. I did expert reviews of the various reports. I also worked as contributing author to other chapters, served as a delegate from Ghana on the IPCC panel. And now that I've moved into the Bureau, Ghana need to delegate another person to be representing Ghana on the panel. I also worked as a TG data member. I was the only African on the team on that group. And now that I am the vice chair, I'm leaving that position as well. So another African need to take up that position. I review the scholarship program, which I still do and I'll continue to do. So contributed to scoping meetings, which I cannot do again now. I do outreach for the IPCC and I can still do. And I get my publications reviewed and cited by IPCC. That I still do and will continue to do. So, ladies and gentlemen, thank you very much for your attention. I'm available for questions.
All right, thank you, Professor Nana. Please, it was a great presentation and a great insight. Thank you for the experience you've given us. Please, I only have one question to ask before I open the floor for others to also ask questions. So with the aerosols, you said it gives cooling effect during the Harmattan, but my question was that I think the aerosol has a two-way system. It can actually contribute to heating and also contribute to cooling in the sense that it can scatter radiations back into the atmosphere. But when there's an existing, let's see, when there's existing temperatures like on the surface and they want to escape, it can also serve as like a trapping mechanism. So I want to know your way about that too, as to whether it only causes cooling or during Harmattan it can also cause heating.
Okay, thank you, Daniel. Yeah, that's a good observation. And I think whenever we are talking about the greenhouse effect, we talk about aerosols as well. So that's a good effect. So good observation. So we're talking about the combined effect, but in any case, I didn't talk about the terrestrial radiation. The focus is on solar radiation. These aerosols are, they block solar radiation, but they are transparent to terrestrial radiation. They are not greenhouse gases. So we have to take note of the difference. The aerosols are not greenhouse gases, or well, if they are transparent to the terrestrial radiation, but they are not transparent to solar radiation. So they block solar radiation. And so that's what gives the cooling effect. So if you look at the combined effect of these aerosols into the stratosphere, the combined effect is a cooling and not warming. So this is different from carbon dioxide and the methane discussions. So for carbon dioxide and methane, they are transparent to solar radiation, but they are opaque and they block terrestrial radiation. So we have to make the difference clear here. Is that okay, Daniel?
Oh, yeah, okay, please. I'm quite cool with that. And the other one too, during one of your submission, you made mention of rainfall during December last 2 years and last year. So I wanted to have your take on what caused it, because we know during those seasons there's actually a northeasterly wind propagating Ghana. So what could have led to the rainfall in those times, since it was dust laden winds?
Okay, so thank you. That is one of the major discussion at the moment. First, or the easy way to start it to say climate change, because the climate system has changed and the season is shifting. But then when you come to physics, we're looking at how these aerosols or Harmattan is having effect on rainfall. I didn't present the results from rainfall because we're still trying to understand how rainfall is responding to Harmattan. When we have less amount of dust in the atmosphere, we get less rainfall. When we have more amount of dust in the atmosphere, we get less rainfall. When we have moderate amount of dust in the atmosphere, we get rainfall like normal, we'll say, or a little bit heavy rainfall. I don't know if you are getting what I mean. But then let's come to physics here. So when we have less dust in the atmosphere, it allows evaporation. It allows evaporation, and so it allows us to get some rainfall. but we don't get as much rainfall as we get moderate dust in the atmosphere, because the same aerosols, the same dust particles also serve as cloud condensation nuclei, or for clouds to form and for rain to fall. So when we have less of it, we don't get too much cloud and we don't get much rainfall. But then we have evaporation. So these two effects do not eventually give as much rainfall as we expect. And when we have too many dust in the atmosphere, it does not allow evaporation that much relatively, but we have so much cloud condensation nuclei, which should be able to help with cloud formation to give us rain. But because we don't have much evaporation, we don't have much water vapor in the atmosphere, we still don't get rain. So, but when we have moderate amount of dust in the atmosphere, it allows evaporation, it allows the amount of dust or condensation nuclei that we need in the atmosphere to give us rainfall. So these are, I mean, this small dynamics I've explained gives us a lot of work to do in trying to understand the response of rainfall to Harmattan season, and even the extra stratospheric aerosol injection, how that will eventually affect rainfall dynamics over West Africa.
Okay, thank you very much. Please pardon me if I'm asking more questions on rainfall, but I have a last one. Please, with aerosols, I know it's supposed to localize rainfall, but with cases of storm, does aerosol still play influence on like rainfall formation?
Yes, thank you. So the answer is a yes. You see, the storm come with wind, and wind will blow the dust to wherever the wind want to blow it to. So where the dust gets to, or the aerosols get to, the radiative effect occur there. It still give the local effect eventually where it ends or it lands or gets concentrated.
All right, thank you very much. Please, my fellow colleagues, the floor is actually opening for questions. So if anybody has a question, we are waiting so Professor answers. Please, you are still waiting for questions.
Hello. Yes, please, I wanted to find out how can we generate our own aerosol, and then maybe if there is any mechanism to spray into the stratosphere to help us to have the cooling effect that we are looking for. Is there a way, or it is still under research? Thank you.
Daniel, can I go ahead and answer?
Yes, please.
Okay, so Hereford, it is already, should I say, technology that's happening. When you go to the Middle East, Dubai, in that area where they can have so much heat and less rainfall, they do what they call cloud seeding. So they fly planes in the atmosphere and they release salt particles, so which also serve as the cloud condensation nuclei, and that helps them to get rainfall when they do that. But of course, it's expensive to fly plane only to release salt in the atmosphere, or like dust in the atmosphere. And so let's say if you want, it's not been raining in Accra and the sun is shining, we have enough evaporation in Accra, and we want rain in Accra, we can fly plane and release salt particles in the atmosphere, and it will rain in Accra. And once it rains, we have the cooling effect as well. So it's already a technology that is being used, it's happening, but it's not so common because it's expensive.
Okay. Thank you very much, Prof.
Thank you, Eford. Please, I'm still waiting for other questions.
Maybe in the chat also.
Please, there's no question in the chat currently.
No, I mean, those who want to put their questions in the chat.
Oh, okay. Please, I can see the hand of Mr. Usman, sir.
Yeah.
So please, you can unmute yourself and ask your question.
Hello, can you hear me?
Yes,
Yes,
please.
please.
All right. Thank you, Prof, for the great presentation. It's unfortunate I'm not contributing so in the office. Yeah, I'm on my way to the office. Yeah. My question is this: impact of Harmattan. Definitely, we know when there is a Harmattan, we have less rainfall, and probably we could have some impact like droughts, and then also even some diseases emerging. The aim of this project is to see how we could reduce the effect of temperature, globally. So my question is, if that is what it aims at, during the presentation earlier, the earlier part of the presentation, you were saying that assuming we have temperatures reducing throughout the whole year as a result of impact of aerosols, the Harmattan, assuming we have a lot of Harmattan impact, reducing the amount of the temperature throughout the whole year. That would be good. But I'm also thinking about the general impact of this whole thing. Because if we have less rainfall, definitely it's going to have impact over our food security. Yes. So, and also based on the third postulate of Newton, because every action has an equal and opposite reaction. So inducing aerosols such as these dust particles into the atmosphere, don't you think that it's going to really have impact? Because that action is going to. So my worry is, what can we give an example in? You said in Dubai, you saying because of that heating over there, so they are trying as much as possible to do let me say the technology to be able to reduce
Okay, Samuel, thank you.
the amount of rainfall. Sorry, to reduce the amount of that part of the world, but the entire activity definitely is going to have, it's going to have an effect over our area. There's going to be a telecommunication connection to everything that we do. So my worry is like, how very effective can this one be?
Okay, thank you. Let me start from the very first one on the global temperatures. So, yeah, definitely during the Harmattan season, naturally what we experience is no amount of rainfall, but we get a cooling effect. So I started with the problem of global warming, and then we're trying to reduce the temperatures in the atmosphere so that the global warming conversation will go down, right? I mentioned that earlier on. Yes, so in science, we try to solve problems, but it doesn't mean that once we solve one problem, we don't create many more. What we normally do is to see what we can trade off and work at it. So thankfully, this solar radiation management is not harmful to the earth. It gives the cooling effect. And on rainfall, as I explained earlier on, for our initial research, we have seen that or observed that when we have less amount of dust in the atmosphere, we get less amount of rainfall. I explained earlier on. So we just need a moderate amount of dust in the atmosphere to give us the normal rainfall that we want. If it is too much of dust in the atmosphere, we get also less amount of rainfall. So that is the dilemma at the moment, which we still trying to understand what it is. In action and reaction, as you said, definitely, it's a new area we're trying to understand. So we can do that to have the local effect or local impact on the local climate, but we cannot tell at the moment the overall impact it will have on the climate system. So it's a new area, and it's only research that will help us to continue to understand the effect that it will have on the main or the overall climate system. So it's an open area for research, and all of us can show interest, have interest, and contribute to it to help us to understand things better. Thank you.
Thank you, Mr. Answer, for your question, and thank you, Madam, for the answers too. Please, does anybody have another question? You are still waiting for.
Okay, so if people get questions in future, they can ask me on maybe through my email or social media handles, and I will answer them.
Okay, thank you. So please, if there are no further questions, before turning on our camera to actually take a group picture, I would like to inform that next month there's going to be the 25th meteorological seminar. So I'll urge everybody to log on. And the video after this will be sent to the participants who actually registered. Thank you very much. Can we please turn on our cameras?
Stop sharing.
Please, can we turn on our cameras?
No, the cup is dark. That's fine. It's okay.
Hello, madam. Good
Yeah.
afternoon.
Becky.
Hello.
Yeah, hello.
Yes. My question is milk and fog considered as aerosol?